students, welcome to the video lecture series on Chemical Engineering Thermodynamics 2. I am Jamin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter number 2, which is a solution thermodynamics. So in this lecture, we are going to discuss about various methods for evaluation of fugacity. So there are mainly three types of method for evaluation of fugacity. First, which is the fugacity and fugacity coefficient from compressibility factor Z. Then second one, which is using residual volume that denoted by alpha. And third one, which is using value of enthalpy and value of entropy. So we can get the value of fugacity and fugacity coefficient using these three methods. Method 1, which is using compressibility factor. Method 2, which is using residual volume. And third method, which is using value of enthalpy and value of entropy. So let's first start with using value of compressibility factor. So fugacity and fugacity coefficient from compressibility factor Z. So compressibility factor can be used to predict fugacity coefficient at lower pressure for real gas, and that can be given by compressibility factor Z is equal to PV upon RT. The Gibbs free energy for real gas and ideal gas we may write as a G is equal to RT ln F is equal to VdP, and for standard state or ideal condition we can write G naught is equal to RT ln F, or can say that for this is for the ideal condition. So fugacity can be replaced by the pressure, so it becomes ln P is equal to VdP. But for the ideal gas we can say that equation of state for ideal gas that can be given by PV is equal to nRT. For 1 mole component it becomes PV is equal to RT. So can say that V is equal to RT upon P. So if we are going to replace this V with RT upon P, then we may write RT upon P into dP. So this becomes our equation number 1, this is our equation number 2, and this is our equation number 3. Equation number 1, which represents compressibility factor. Equation number 2, which is for the Gibbs free energy for the real gas, and this equation number 3 is for the Gibbs free energy for the ideal gas. In ideal gas, fugacity replaced by the pressure, and we can use this VdP. So this V is the ideal volume, so we can replace this ideal volume by RT upon P. So it becomes our equation number 3. By substituting this equation number 3 from 2, we will get G minus G naught is equal to RT ln F upon P is equal to VdP minus RT upon P into dP. So if we are going to subtract equation number 3 from equation number 2, we will get this type of equation where G minus G naught is equal to RT ln F minus RT ln P. Ln F upon ln P we can take common RT, so RT into ln F minus ln P, which become ln F upon P, and here VdP minus RT upon P into dP. So this is how this equation becomes. Now let again rearranging this equation, we will get RT d ln F upon P is equal to V minus RT upon P into dP. Taking integration, we will get RT ln F upon P is equal to integration of 0 to P V minus RT upon P into dP. Now taking RT To this side we will get ln f upon p is equal to integration of 0 to p v upon rt, multiplying rt to this side, so we are getting v upon rt minus rt cancels, so can say that 1 upon p into dp. Multiplying and dividing with p, we will get the ln f upon p is equal to, so if we are going to multiply and divide by p, we will get ln f upon p is equal to integration of 0 to p pv upon rt upon p. So here we are going to multiply with p and divide by p, so this pp becomes cancelled, so it becomes 1 into the dp. So here we are going to multiply with p and divide with p. So if we are going to multiply with p, then it becomes pv upon rt. This pp becomes cancelled, so it becomes 1 upon p. So this equation becomes ln f upon p is equal to integration of 0 to p into z minus 1 upon p into dp. Here taking z, because we know that compressibility factor that denoted by pv upon rt. So this term is replaced by compressibility factor, so can say that z minus 1 upon p. So here it becomes z minus 1 upon p into dp. So this equation is used for the find out the fugacity and fugacity coefficient. We know that fugacity coefficient that can be represented by f upon p. So can write that ln phi is equal to integration of 0 to p z minus 1 upon p into dp. So this is the method number 1, which we can use compressibility factor to find out the fugacity and fugacity coefficient. Now let's discuss about the second method. In second method, we are going to use the residual volume or to find out the fugacity of gas, or can say that let's first write method 2 using residual volume. So fugacity of gas that can be defined by dg is equal to vdp is equal to rtd ln m. The residual volume alpha is defined as a difference between real volume and ideal volume. So can say that alpha is equal to real volume minus ideal volume. So we know that if we are going to apply equation of state instead of this v, then we can replace this v by RT upon P. We cannot use the equation of state for ideal gas for the real gas. So we are only just replacing this ideal volume. We cannot replace this real volume using equation of state for the ideal gas. We have to use, if we are going to replace this real volume, then we have to use real equation of state such as the Rayleigh-Kwong equation of state, or Penn-Robinson equation of state, or for van der Waals equation of state. But there are no need to replace this real volume. So we are just going to replace this ideal volume by RT upon P using equation of state for ideal gas. Now let's take this is our equation number 1 and this is our equation number 2. So substituting this equation number 1 into 2, we will get alpha is equal to, substituting equation number 1 into 2, we will get alpha is equal to RT d ln f upon dp minus RT upon P. So here we are going to replace, this is a equation for the real gas because we are going to use fugacity. So if we are taking V is the subject, so we can write that RT d ln f upon dp. For this V, if we are going to make subject as a V, so we are going to replace this real V with this equation number 1. So if we are going to put the value of equation number 1 or using equation number 1 in this equation number 2, we will get alpha is equal to RT d ln f upon dp minus RT upon P. Now taking RT common, so this equation becomes d ln f upon dp minus 1 upon P. Now taking RT to this side, so we will get alpha upon RT is equal to d ln f upon dp minus 1 upon P. So rearranging this equation, we will get d ln alpha is equal to alpha upon RT plus 1 upon P into dP. So what we have to do here, making subject of d ln f, so we can say that this 1 upon P going to this side, so it becomes plus 1 upon P, so alpha upon RT plus 1 upon P, and taking this dP to this side, so it becomes like this. Now again, if we are going to rearrange this equation, we can say that d ln f upon P is equal to alpha RT into dP. So if we are going to take integration, we will get ln f upon P is equal to 1 upon RT integration of 0 to P alpha dP, where alpha is a residual volume, or can say that real volume minus ideal volume. So this is the equation to find out the fugacity and fugacity coefficient from residual volume. If we want to find out fugacity coefficient, then this equation becomes ln phi is equal to 1 upon RT integration of 0 to P alpha dP, where alpha is a residual volume. So these both equations used for the find out fugacity and fugacity coefficient. Now let's discuss about method 3, which used for the find out fugacity from using enthalpy and entropy. Enthalpy which denoted by S and entropy which denoted by S. So if we are going to use enthalpy and entropy, the difference of Gibbs free energy in standard state and at the real state, that can be given by, for the real gas, Gibbs free energy G is equal to H minus Ts. So can in term of fugacity we can write RT ln F. Now if we are writing at standard state, then G naught is equal to H naught minus T into S naught is equal to RT ln F naught. Gibbs free energy at standard state, this equation number, so let's suppose this is equation number 1 and this is equation number 2. This was at real state, and this equation number 2 for the standard state. So using equation 1 and 2, can say that G minus G naught is equal to H minus H naught minus taking T common, so we will get S minus S naught is equal to RT ln F upon F naught. So if we are taking G minus G naught, so it becomes G minus G naught H minus Ts. So first taking H minus H naught, then so this becomes like this, minus taking T as a common, so taking T as a common, S minus S naught by taking minus common, so it becomes like this, and RT ln F upon F naught, so taking RT common, ln F minus ln F naught may write like ln F upon F naught. So this is how this equation becomes. Now rearranging this equation, we will get RT ln F upon F naught is equal to H minus H naught minus T into S minus S naught. Again, if we are going to rearrange this equation, it becomes F upon F naught is equal to 1 upon RT into H minus H naught minus T into S minus S naught. So this is how we can use the enthalpy and entropy for the find out fugacity and fugacity coefficient. If we are going to replace this F with P naught, then it becomes fugacity coefficient. So this is how we can use the equation for find out fugacity and fugacity coefficient. So this is all about today's lecture. I am completing my lecture here. Thank you.